Okay. Howdy. Welcome to Texas A&M Institute of Data Science Tech Talk series. My name is Jian, an assistant professor from the College of Performance, Visualization, and Fine Arts. I'm also the assistant director of Texas A&M Institute of Data Science and the director of the Digital Twin Lab at the Institute. So today, it is our pleasure to welcome Dr. Tuhin Mukherjee from Iowa State University to give a talk on applications of computational tools in metal additive manufacturing. So Tuhin Mukherjee is an assistant professor of mechanical engineering at Iowa State University. Previously, he was a postdoc researcher in the Department of Material Science and Engineering at Penn State, from where he also got his PhD. He is the author of many papers in leading journals, including Nature Reviews Materials, Natural Materials, and Progress in Material Science. He authored an edited book entitled The Science and Technology of 3D Printing in 2021, and a textbook on theory and practice of additive manufacturing in 2023. He served as a guest editor and editorial board member on various journals, so I'll not list all of them. He was awarded the American Welding Society Research Fellowship and the Robert Tuhin Research Excellence Award by Penn State. So with that, please join me to welcome our speaker today, Dr. Tuhin Mukherjee. The microphone is yours, Tuhin.
Thank you, Dr. Tao, for a very nice introduction. And a warm greetings from Ames campus of Iowa State University. It's in central Iowa. So as you know that 3D printing or additive manufacturing is a rapidly emerging field for making complex and intricate parts, metallic parts. And computational tools like multiphysics modeling and AI tools are supporting for that rapid growth. So in my talk, I am going to talk about several applications of those computational tools in metal additive manufacturing. In particular, I'll point out several uniquenesses and opportunities that we have today with metal additive manufacturing, and then justify why we need those computational tools for the rapid growth of additive manufacturing. And then I'll give you 7 examples of the applications. And then I'm going to finish with future perspective and future impacts. So this left-hand example, many of you may know. In 2014, in the International Space Station, they needed a range like this. But that time, NASA didn't have any plan for supplying mission. So what they did, they sent a 3D design of this range from Houston, Texas, very close to where you are sitting now, to the International Space Station. And in the International Space Station, they had a 3D printer that printed fully functional range. Even 10, 15 years ago, this could have been a science fiction. But now, because of 3D printing, it's happening in reality. And if you see, the application of metal additive manufacturing is in diverse industries, starting from aerospace, consumer product, energy industry, medical industry, so on and so forth. Then what is the problem that we are going to talk about today? The main problem is, if you are from metallurgy, you know that there are over 5,000 commercial metallic alloys. And how many of them we can print today? You can probably count with both of your hands. That few. And why that is so? That is because we are still unable to properly control microstructure, mechanical properties, and defects of additive manufacturing parts. What do I mean by that? So when we 3D print a metallic part, the microstructure can look strikingly different depending on how you are making it. For example, the top picture, you can see that the grains can be very long. Okay, we call it columnar grains. And when this kind of part is under tensile loading, two consecutive grains may start separating from each other, leading to failure of the part. But that's not the case when you have very small grains that will provide enough strength preventing failure. So you see that depending on how you are printing, your microstructure look different, and that will result in very different mechanical properties. In the same part, depending on the location inside the part, the mechanical property can significantly vary. For example, you see with the distance from the top of the deposit, the hardness varies significantly. And that is also attributed to the difference in the microstructure. And finally, a wide variety of defects, starting from lack of fusion voids, porosity, cracking, surface roughness, distortion, so on and so forth. All of these can significantly degrade the mechanical properties, serviceability, performance, reliability of the part. And when we spend a lot of money in 3D printing a part by using $1 million expensive equipment, then we do care about our part. We don't want to print and throw that part away. So that's why controlling all of these things are really, really important. And that's where the computational tools can help us. Let me give you a quick example. If you do a metal 3D printing, these are the variables that you can adjust. Like for example, power, speed, laser beam radius, layer thickness, and there are many variables that are process conditions or properties of materials. Now, there are 12 in this list, and if you use a very simple two-factor design of experiment, the minimum number of experiments that you need to fully capture the effects of all these variables is 2 to the power 12, which is 4096 experiments. Now, if you do 3D printing, you know how challenging 3D printing experiments are. So let's assume that you do one successful experiment a day. A PhD student cannot graduate in 10 years. So that's the issue. And if you just take two process parameters, laser power and scanning speed, you see for the same material, the power and scanning speed vary depending on which additive manufacturing process you are using. Please note that both of them are plotted in log scale. So that means you need to explore such a wide range of processing conditions to be able to fully explore the effect of processing conditions and to understand and correlate those with microstructure, properties, and defect formation. To do so, we can take advantage of computational tools that can virtually test this process parameter window and reduce the parameter space for experiment. So it can tell what works and what does not work so that you don't waste material and energy and time in doing experiments that are not fruitful. In other words, it will minimize trial and error, improve quality, and at the end, reduce money. So what do I mean by computational tool? So it can include multiphysics modeling as well as AI tools such as machine learning and deep learning. So how they help? Mechanistic modeling calculates the variable that affect the three things that I was talking about by providing scientific insights. And it can guide experiments by providing the appropriate conditions for which we, let's say, get defect-free part with appropriate microstructure and properties. But development of these models depends on proper understanding of the science behind additive manufacturing process. Now, you know, additive manufacturing is a rapidly emerging process, and for many cases, we do not understand the physics completely. Then what we do, we take advantage the wealth of data that we generate every time we run the model or every time we do the experiment and synthesize those using machine learning to obtain understanding that we cannot obtain from mechanistic modeling. And these days, machine learning algorithms or deep learning algorithms have been improved so much that they can provide reliable prediction with less data. And most importantly, since we are talking about multivariable problem, machine learning can also guide us to understand which variable is less important, which variable is more important, so that engineers can know which variable to control to be able to tune in microstructure properties and defects. So at Iowa State, we do a wide variety of things in both the domains, modeling and machine learning. So let's start talk about the modeling. The most primitive model that we do is reduced order analytical model. So it has a lot of approximations to accelerate the computational speed, but it can give us essential information on which microstructure property and defect depend on, like, for example, the temperature distribution or the dimensions of the molten region. So this is an example of laser-directed energy deposition additive manufacturing, where you see a very primitive reduced order analytical model can more or less predict the molten pool or deposit dimensions within acceptable limit. For laser powder bed fusion, and this is from a recently published paper with my student, you can see that they can capture not only the effect of process and process conditions, but the differences in the materials. So A, B, C, and D are for 4 different materials: stainless steel, titanium alloy, nickel alloy, and aluminum alloy. And you see, depending on the differences in their thermophysical properties like density, thermal conductivity, specific heat, so on and so forth, they exhibit very different looking molten pool. And the temperature inside the molten pool is also quite different. So the advantage of these type of analytical models are they can not only provide useful insight of this process, but it can also be used for comparing different alloys in terms of their fusion zone geometry, cooling rate, evolution of microstructure, susceptibility to defects, printability, so on and so forth. Now, if we add a little more complexity into it and we develop numerical models, okay, why? When we need to understand a more in-depth knowledge about additive manufacturing process. For example, when we create a molten region, how that molten metal flows inside that region. Okay, so when we create molten region, depending on the temperature difference, there will be differences in density, differences in surface tensions. All of those drive the convective flow inside the molten region. And these convective flow not only affect the dimension of the molten region, but the temperature in the nearby region, and thus the evolution of microstructure. So this type of model, in-depth numerical models, can provide us a very detailed picture of what's happening during the additive manufacturing process. Now you can understand that if you look at the scale bar, this is 0.5 millimeter. That means this is something like 5 millimeter long. So whatever is happening is within a very small, tiny domain. Okay, we are capturing detailed physics within that tiny domain. Now we know that we make additive manufacturing parts by depositing many layers and many hatches, thousands of layers and hatches. So what if we want to simulate the entire part? That's often very difficult with such an in-depth model, for which we develop part scale model that does not consider so much about what's happening inside the molten pool, but is much more interested in looking at the entire picture. So let me play this animation and you will understand what I'm saying. Like, for example, the laser beam in laser powder bed fusion is moving in a zigzag pattern. And this model is successfully capturing the variation in the temperature field that's happening across the entire part. So that means for the entire part, depending on where we are looking at, we can accurately predict the temperature fields and its spatiotemporal variations. You see, this is an example of stainless steel part made by laser directed energy deposition additive manufacturing, where the part is 40 millimeter long, 40 millimeter in length, and 10 millimeter in width. Okay, and this part is made by thousands of layers, and there is no finite element or finite volume method or model that can model the deposition of the entire part. It's not possible. So that's why we need to use part scale models that are based on several approximations, but can give you the temperature fields and other essential information within a realistic acceptable limit. So from part scale model, if we go forward and try to understand that what are the needs, whether this is a reduced order model, a much more in-depth numerical model, or a part scale model, the main objective is to get the temperature fields and cooling rates. Now, once we know those, we can take advantage of those information and get solidification morphology, whether columnar grains or equiax grains that I was talking about, or whether it's a complete 3D grain structure, not only giving you the grain size, but its grain size distribution in 3 dimensions, and also residual stresses and a wide variety of defects. So this is the overall objective, and this is the main mantra of developing a wide variety of mechanistic models for additive manufacturing processes. Now, at the same time, if we look at where machine learning can help in additive manufacturing, to me, there are 2 types. Like all other machine learning applications, for additive manufacturing also, we can classify all the problems that we want to address into 2 classes: regression problems and classification problems. And under regression problems, the examples are like control of geometry, whether we are making a larger molten region or smaller molten region, whether the grain size are very big or small because they affect properties, how much residual stress we are accumulating, what is the amount of distortion that we have in those parts. Those are regression problems where we talk about the particular value of a variable. In contrast, in classification problems, we talk about 2 or multiple classes, like whether our part has porosity defect or this is defect free, whether it has crack or it's crack free, whether the solidification morphology is columnar or equiaxed. So it's a classification problem. And depending on these 2 types of problems, we use different machine learning algorithms, like any other applications of machine learning. So now in subsequent slides, I'm going to give you 7 examples of the use of modeling and machine learning in additive manufacturing that we are doing at Iowa State. So this example is very close to my heart, and the picture that you are showing is actually in the building where I'm sitting in my lab. We have a wear arc additive manufacturing system, and that is controlled by a cobot or a collaborative robot. What is the advantage and what we are doing? I'm coming in a minute. But what it does is it deposits material in the form of wear, which is melted by a high energy electric arc. Just like this, the electric arc is melting the wear, metallic wear, and that is being deposited in layer by layer and making the part in 3D. So this is my student wearing all the PPEs, observing very closely what's happening in real time. So collaborative robot or cobot is much better than traditional robot in many cases. Like for example, it reduces the need for path programming, enhances the safety of human interaction, and improve the user friendliness and productivity. And because of these, it's particularly useful for additive manufacturing. So what it does, as you see, my student is doing, you do not need to program this robot explicitly. Instead, you can teach this robot a path along which you want to deposit the material by selecting a few important coordinates. And then the robot itself will identify the deposition path and 3D print the entire part. So here we model the additive manufacturing process using collaborative robot. I can give you one quick example here. Like we deposit the material following a hexagonal pattern, and the cobot needs to be programmed just based on the 6 vertices of this hexagon. And you can see that corresponding temperature calculation using a part scale model, the deformation calculation, and stress calculation, all are using part scale model, because here we are talking about large length scale. And you can see that the part scale model can give you the essence of the process itself, where the stresses are accumulating the most, how the part is distorting in 3D, all those detailed information. The second example that I have is consistent with one of our objectives, structure, property, and defects. It's on controlling grain structure. So if we go back to our metallurgy class, we are taught that during solidification of an alloy, there is a two-phase region, solid liquid region. So when the liquid is being solidified, not all liquid instantaneously becomes solid. There is a two-phase region, liquid and solid. So if you plot the temperature in that region, you will see there are two things. One is actual liquid as line, and the other one is the equilibrium liquid as line. And the difference between these two is called supercooling. So for all solidification process to happen, there has to be a supercooling that will drive the solidification process. This temperature difference is very important, because this temperature difference divided by distance, which is called temperature gradient, represents whether we will form columnar grains or equiax grains. So this is a very well-known plot from metallurgy book, where people plot this temperature gradient, which is nothing but temperature difference divided by the distance, the slope of this line, with respect to growth rate. Growth rate means how fast this solidification font is moving, the rate of solidification. You see, depending on the slope of this plot, you can identify how the solidification morphology will look like, whether this is planar, cellular. We have talked about columnar and equiax. You can very easily find out. What you need to do, you need to just calculate the temperature distribution that I showed you how to calculate. Once you do that, you get the temperature gradient and growth rate and readily find out your solidification morphology. Second advantage, you see along this hyperbolic line, G times R, which is temperature gradient times growth rate, is constant. And that value gives you the size of the grain. This product is called cooling rate, and that is directly connected to the size of the morphology. Now, let me give you examples of both of these. See, here we have used a model to calculate the G by R ratio for an aluminum alloy, 6000 series aluminum alloy. Now, you see that the calculation is saying us that this G by R ratio, which is the slope of the previous plot, is varying spatially like this. Now we know for this material, there is a critical G by R value that determines whether it will form columnar grains or equiax grains. For example, if the G by R ratio is more than 9, it will form columnar grains. If this is less than 9, it will form equiax grains. Now you see, this is the computed value of G by R. In this region, the value is less than 9, and they should form equiax grain, which is proven here from the model as well as from the experiment. Beyond which, you see the value is more than 9, that means columnar grain. You see long columnar grains are being formed, which is also evident from the experiment. So this is giving you a very good examples of how you can take advantage of temperature calculation and process it and get useful scientific insight to be able to predict microstructure. So this is about the morphology. The next thing is about the size. Now, if I go back once again to our phase transformation class, we often talk about primary dendrites and secondary dendrites. For non-metallurgists, they look like Christmas trees, but that's how solidification happens. And the distance between two consecutive primary dendrite arms or distance between two consecutive secondary dendrite arms, they significantly contribute to the mechanical properties of the part. So we need to somehow predict these values. How we can do that? Easy. From the previous calculation, we find out GR, which is cooling rate. And from solidification literature, like if you take Mott Fleming's very famous solidification book, this formula is coming from there. Secondary dendritic arm spacing, which is this distance, is related to the cooling rate using this formula. Now 50 and 0.4, they are alloy specific constants. For steel, this is 50 and 0.4. If you are taking aluminum alloy or nickel alloy, they might be different. So once you have these and calculate the cooling rate from the temperature field, you can calculate secondary dendritic arm spacing. And you see here for different laser power, I show here that how we can calculate the secondary dendritic arm spacing that is matching with the experiment. For low power, you see smaller dendrites, and for high power, you see larger dendrites, which is very consistent with the calculated results. So now, since we have talked about the microstructure, the next example that I selected is for controlling one of the very primitive mechanical properties, which is hardness. And the example is for a ferritic steel whose hardness is affected by martensite. So often we weld or we additive manufacture this type of part by using multiple tracks. Okay. And here we are talking about a ferritic steel grade 91 that is used for nuclear power industry. This is a famous transformation diagram. And you can see that martensites form for this particular material at a very low cooling rate, 0.05 Kelvin per second. And in additive manufacturing, what is the cooling rate? It's like 10 to the power 3 to 10 to the power 5 Kelvin per second, depending on the processing conditions. So this is guaranteed that whenever you process this material using additive manufacturing, you will end up having martensite. And this martensite will control the hardness of the part. But there is a small catch. We make additive manufacturing part by depositing many layers. That means the layers that is already deposited will undergo repeated heating and cooling. And that repeated heating and cooling changed some of the martensite to tempered martensite. Hardness of tempered martensite is less than martensite. So that means depending on how many times it's getting reheated and cooled, the extent of tempered martensite formation will be dependent on that, and hardness will accordingly change. So how to model that? What we did, we used the isothermal aging data. Okay. Now, for a complex material system like grade 91, it's very difficult to get reliable data on isothermal aging. So what we did, we collected a lot of data from the literature and then used those data to train a neural network, and then use those neural network to generate a lot of tempering data for different time and temperature combinations. Once we have that, what we do, we get the constants in Johnson-Mehel-Abraham equation. What's this equation? If you don't know, it's an equation, very famous equation for capturing isothermal phase transformation. Okay. So on the other hand, the model that I was talking about can give you the temperature variations with time, multiple thermal cycles, repeated heating and cooling due to deposition of multiple layers and tracks. Now, JMA equation is an isothermal phase transformation equation. So what we need to do, we need to take that and integrate over the temperature variation with time. And that will give us the tempering kinetics as well as the hardness of part. And it looks like this, where hardness is plotted for grade 91 steel part made by laser directed energy deposition with respect to the distance from the substrate. And you can see that near the top, the hardness does not vary significantly, but then down below, it varies linearly with the distance. And this phenomena, which is observed both in experiment and in calculation, can be explained by using model. For example, when we are talking about near the bottom region, you see that the peak temperature is going below the AC1 temperature. What is the AC1 temperature? AC1 temperature denotes the region between austenite and martensite. So if you think of the phase diagram of steel, that's the important temperature that we often talk about. So the transformation from austenite to martensite will be valid even only if the temperature is below this AC1 temperature. But you see, for this case, for first 4 cycles, whatever martensite it forms, it goes back to austenite because the temperature goes beyond 1100 degree Kelvin. But after some time, the peak temperature is not going beyond AC1 temperature, and whatever martensite it forms, it undergoes repeated heating and cooling, and those martensite transforms into tempered martensite. So that's why the hardness is less than the top region. What's happening in the top region? The peak temperature never goes below AC1 temperature. So the martensite that forms here will transform again back to austenite. So this martensite will never transform into tempered martensite. That's why the hardness in this region is controlled by the absolute amount of martensite, not tempered martensite. Okay, so a very complex metallurgical phenomena we are trying to capture by using this kind of process model. So the fourth example, so after structure and mechanical property, now we are going to the defects, and example 4, 5, 6, and 7 will be focusing on defects, different types of defects. So first one is reducing porosity. Now there are 3 different types of porosities that we encounter during additive manufacturing process. First one is lack of fusion. What do I mean by that? we deposit multiple tracks. What if they do not properly fuse with each other? And that will end up creating lack of fusion defect. Second, often we perform additive manufacturing in keyhole mode. What do I mean by that? The energy density is so high that it forms vapor cavity during the process. And if that vapor cavity or keyhole is unstable, that will break and generate lot of gas bubble that will end up creating porosities. And the third one is gas porosity, where the shielding gas or metal vapor are trapped within the molten region and create porosity. You can see they vary widely in terms of their shape, size, and morphology. So here I'm going to talk about lack of fusion and gas porosity. So like all three types of porosity defects, lack of fusion defect, which is represented by improper fusion among tracks, significantly deteriorate the mechanical properties. As you can see, the ultimate tensile strength decreases very rapidly with the size of the void. So how we model those? This is a typical example of the molten region, okay, or the track. Now, if you see the transverse section of the molten region, it looks like half of a watermelon. And that is the transverse view of one particular track in additive manufacturing. Now we make a part with many such tracks, and it should look like this, where those small watermelons are just like this, collection of many watermelons. So what do I mean by lack of fusion void? Lack of fusion void are this white region, where the molten pools, two consecutive molten pools are not properly fused together and creating empty region. How you can minimize this? One way to minimize is bringing them close. And that distance is called head spacing. That means if you reduce the head spacing, you should reduce the lack of fusion void, and which is very consistent with the experiment. You see, void fraction is significantly less at a low head spacing. So like head spacing, there are many other variables that contribute towards lack of fusion void. And some of those are here in this list. Like head spacing, I have talked about. Pool size, also very important. Marangoni number, that talks about the fluid flow inside the molten pool, peak temperature inside the molten pool, and Fourier's number that determines or that indicates the heat transfer in the additive manufacturing process. Now, if you have all these variables somehow calculated using an additive manufacturing model, we can even get a linear regression model and propose an index that can delineate between the porosity cases and cases where the porosity is very less. So that's the advantage of combining modeling and machine learning, and to identify very important scientific insights to be able to solve such a complex problem like porosity defect in additive manufacturing. So the other type of porosity is called gas porosity. Now, there are two times that are important, time to rise and time to solidify. What are they? Let's imagine this is the molten region and we have a gas bubble. Now, this gas bubble, since its density is less, density of gas is less than density of liquid, because of buoyancy, this gas bubble will try to float up, rise up. Now, before it can rise up and escape from the molten pool, if the molten pool solidifies, then they will be trapped and cause porosity. So then the time it takes to rise up, time to rise, and times the molten pool takes to solidify, both are important. Okay, so if time to rise is significantly higher than the time to solidify, then definitely you are going to form porosity. So what we did, we tried to calculate these 2 times in additive manufacturing and try to come up with their ratio and propose a dimensionless index. What we found? Depending on the index, we can classify the cases where we see porosities and the cases where we do not see porosity. We have about 100 experimental cases for 4 different commonly used materials, and these 100 data points are collected from the literature, different papers that are available. And we see that no matter what process parameters we are using, at the end, a simple time ratio can delineate the defect-free cases from the defective cases. And when we have defect, the index is also useful to represent the density or 1 minus porosity, that number very accurately. So here, this is another great example where a simple temperature field and molten pool dimension calculation can give you so important insight to solve very important problems. Okay, the next example is minimizing residual stress and distortion. So I think probably residual stress and distortion are 2 most important problems in additive manufacturing, because in additive manufacturing, we try to print dimensionally accurate complex part, and we don't want our part to distort. So what we did, we start from temperature field calculation, and then take that temperature field calculation along with the geometry and mesh, take that to a mechanical model, finite element based mechanical model, and calculate residual stress and distortion. So that type of modeling framework is enormously useful to provide scientific insights. For example, you see how the distortion or deformation field is evolving depending on the temperature. This is the temperature field, and this is the deformation field. You see, where the temperature is very high, the deformation is also high. Why? This is alpha delta T, high school physics. As the molten pool is progressing, this deformation field is also getting elongated. So this information is very useful to find out how much deformation you can get in the final part, and whether this is exceeding the allowable design limit. Similarly, for residual stress, we can get the spatial distribution of residual stresses, like how the high residual stresses that are accumulated after the deposition of second layer is partially alleviated when you deposit subsequent layer and reheat and recool it, and how residual stress is spatially so non-uniform, causing delamination, cracking, and many other problems in additive manufacturing, and how numerical model can capture all of those elements and guide engineers to overcome all these problems. Now, going back to one of the primary advantages of using machine learning. So that was identify the relative importance of important variables. What we did, we identified 5 physical factors that control or that affect residual stress formation. And we created a database of 243 data for 3 very commonly used alloys. What we found, delta T, which is nothing but the difference between solidus and preheat temperature, is the most important variable controlling residual stress. If we go back to welding literature 40 years ago or 50 years ago, we will see that in welding industry, it's very common to preheat the welding plate before welding. What they are doing, they are increasing this T preheat to be able to minimize delta T, to minimize residual stress. So you see that using modeling result, then teaching machine learning algorithms using those modeling result, we are finding out signs that are there in the welding industry for long time. That means these computational tools are enormously advantageous to be able to give you those insights that are already proven for a long time in the industries, in various industries, but at the same time, discovering new science moving forward and helping us to be able to solve important problems in metal additive manufacturing. Sixth example. So when we do additive manufacturing, we are here talking about high temperature process. Just imagine the molten region as your coffee cup. Water vapors, water molecules evaporate from the top surface of the coffee cup. Similar thing happens for a molten pool. The alloying elements vaporize from the molten region, and at the end, the chemical composition of the part is significantly different from the material you started with. For example, you see, this is an example of welding aluminum alloy, 5000 series. Magnesium is one of the prominent alloying element for 5000 series aluminum alloy. And because of evaporation, there is a depletion of magnesium concentration. What does it do? It not only changes the composition, but it also changes the microstructure, mechanical properties. And if you are talking about stainless steels, it also affects the corrosion resistance. So all important properties that are related to serviceability, reliability, and performance, they are affected by this. So this paper just became online yesterday in NPJ Computational Materials. So what we did, once again, we started from very basic temperature calculation. And then we know the vapor pressure versus temperature relation, and this is a material property. For different elements, we see different plots. It does not depend on whether additive manufacturing or welding. It's a material property. So based on this relation and calculated temperature field, we get vapor pressure distribution. And then in an alloy, we have different composition of these alloying elements. Depending on that, they have different thermodynamic activity. So thermodynamic activity and vapor pressure gives you partial vapor pressure, which is responsible for evaporation. So once we can calculate the evaporative flux of individual elements, we can calculate the final composition change. And you see, for nickel alloy, a nickel-based superalloy that consists of many elements like chromium, cobalt, titanium, aluminum, nickel, tungsten, we can calculate their evaporative fluxes. And depending on the relative difference of evaporative fluxes, we can find out the composition change, and which is very consistent with the experiments that we performed for a wide variety of elements. So the last example that I have, and I have 10 more minutes to finish this talk. The last example that I have is reduction in surface roughness. So why surface roughness is important? See, we talk about additive manufacturing of very complex part where dimensional tolerance is very important. Like, for example, this implant from our department, or where we talk about bone implant that looks like this. So one way to achieve good surface roughness is we use very thin layer. In additive manufacturing, we use layers that are thinner than human hair. But if you can reduce the layer thickness, even small, then you should be able to reduce the roughness. But at the same time, if you print your part with very thin layer, you will slow down the productivity. It will take more time. So there has to be a trade-off. And to achieve that trade-off, we need modeling and machine learning. What we did, we identified scientifically why surface roughness falls. And we came up with 3 different factors. Geometric factor that talks about how the tracks are deposited, instability factor, whether the molten pool is continuous or discontinuous, and then whether the molten pool will be uniform or disintegrated into small balls and create surface roughness. So all these things we calculated, and parallelly we also measure the surface roughness using a surface measurement method in this campus. And then we got the entire picture of the surface profile representing the surface roughness. So this is the part, printed part. This is the top surface. And within this region, we did the surface measurement using optical scanning to get the surface topography. Now, this surface topography data was correlated with the index that we proposed, or the dimensionless surface quality number, based on those three scientific factors. And you see, we can very accurately came up with a process map that will guide engineer how rough the surfaces will be. For example, here in the x-axis we have heat input, y-axis powder mass flow rate. So if we deposit for same heat input, if we deposit more powder, the surface is going to be rough, very intuitive. Or if we have same mass deposition rate, we increase the heat input, we are going to create non-uniformity and increase the surface roughness. So higher number in surface quality number representing rougher surface. Two experimental case, B and C. C has higher number, higher surface quality number, creating rougher surface. So this is an example of how you can use modeling, and these results are coming from a reduced order model. So these calculations are very rapid, but still able to give you some understanding of the surface roughness and how to control those. So closing the deal, what are the major contributions of using modeling alone, machine learning alone, or sometimes combining both of them? First, we have methods to control grain structure, solidification morphologies, and other attributes of microstructure. Since we can control microstructure, we can provide insight about the spatial inhomogeneity of mechanical properties, which is a characteristics of additive manufacturing part, and how to reduce that. And finally, we have talked about 4 defects, but there is no limit. We can use similar methodology to be able to minimize all common defects in additive manufacturing. So summing up, this technique of using computational tool can not only provide improved scientific understanding of the evolution of microstructure properties and defect, but also give us the method to control them. So where we can go from here? And this is something that is very close to Dr. Tao's heart, digital twin. So this is a very primitive idea of digital twin we proposed 5 years ago, that how digital twin of additive manufacturing can look like. Now across the world, we are still making the building blocks, but we yet to make a fully working digital twin that can solve all problems of additive manufacturing in terms of microstructure properties and defects. But you can see the building blocks that we are talking about, like the computational tools, mechanistic models, machine learning, are integral part of the digital twin. And the second example that I think is going to be the future is the use of quantum computing. Why? See, we are talking about challenging computing technologies like the numerical models and part scale models. They need heavy computation. And what else can help you than a quantum computer? And already this link, if you go to this link, IBM is talking about, and I am quoting from IBM's website, that quantum computing will disrupt and redefine the manufacturing. This is IBM's website. And SBIR, if you do not know, it's Small Business Innovation Research in the US, that funds small business initiative in this country, that also has recently emphasized the importance of quantum computing in 3D printing. So these two examples are telling us that that's the future. Use of quantum computing is the future for the growth of additive manufacturing, especially when we consider the use of computational tools. So I have 3 last slides. This is a recent textbook on theory and practice of additive manufacturing, and I am very happy to show it wherever I give talk. So this book also has a chapter on the use of computational tool, some of these things that I have talked about. So if you are an instructor and teaching additive manufacturing course, you can scan this QR code and you can request a copy for instruction. And last but not the least, some of these things that I talked about are we try to put those as educational content and research content on our YouTube channel, which is called Science and Technology of Advanced Material Processing, STEM, and the YouTube handle is @STEM group. So if you have a cell phone, you can scan this QR code and it will direct you to that. We are still growing, but we have started putting the educational content for everyone to take benefit from. And at the end, these are the people who work, very hard and diligently behind the scene to make all these things that I explained happen. So thank you very much for patiently listening to me. And if you scan the right-hand side QR code, it will direct you to my LinkedIn page. And if you have any questions now, I will be very happy to answer. And if you have any question in future, just drop me an email or connect via LinkedIn. I will be very happy to answer that. So thank you very much.
Wow. Thank you, Tuhin. And let's thank our speaker for the wonderful talk. And any questions? Feel free to unmute yourself. You can answer. You can ask question directly. Ankita, we cannot hear you. Are you going to answer any question? Ask any questions? We cannot hear you for some reason. You can type in your question, maybe.
So I think she's writing on chat box, but
yeah,
I cannot open the chat box. So Dr. Tao, would you mind reading it for us?
Yeah, I'll read the chat box. She just typed, can you hear? We cannot hear you for some reason. You can type in your question, I'll read out. So while Ankita is typing, any other questions? So I do have a question from, I've been trained as a computational physicist mostly, and I didn't do much experiments and almost done zero, advanced experiments. And one thing I just curious about is this temperature profile and the structure profile. Are there any tools you can directly measure the temperature inside with some profile? There are some measurements or some techniques you can use to give you a profile reading directly of the temperature inside.
Right. What I believe is the proof of pudding is in eating, right? So definitely all the models that we develop or we claim to develop, they need to be calibrated and at the end validated with experiments, right? Because the objective, we are manufacturing engineer. The final objective is to make the part, right? So the answer to your question is yes, but with different extent. What do I mean by that? People use thermocouples, okay, that are attached to the part in different locations and try to get the temperature data. But that thermocouple measurement has problem because thermocouples are known to suffer from poor temperature resolution. And also in additive manufacturing, we are talking about the temperatures are like, 2500 Kelvin to 3000 Kelvin. No thermocouple can sustain that high temperature. Okay, so what's happening inside the molten region, we cannot measure using thermocouple. For that, we have IR measurements. Okay, thermal camera, IR cameras, they can measure some temperatures, but they are mostly restricted in measuring temperatures on the top surface because they cannot see what's happening inside the molten region. So yes, there are ways, but they have their relative, advantages and disadvantages.
Sure, I see.
Can you hear me now?
Yeah, we can hear you
Yes.
now.
Yes.
Go ahead.
Hi, Tuhin. Such a wonderful talk. I had two questions. So the first one is similar to the question which Dr. Tao asked. So I wanted to understand, like when you have a thermocouple, suppose if you are building a big part versus if you are building a small part. So if you are building a big part, for the laser to come back to the original location, it's taking much more higher time compared to building a small part. So when you are mapping the reheat cycle in the modeling, how are you measuring like when the laser, the time lag between two layers, like how much is it solidifying or cooling when the laser comes back next?
Okay. Yeah. So, it depends on the process itself. Like, let me give you a very straightforward example. Let's say you have a track which is 10 millimeter long, okay?
Mm-hmm.
And you are going at a speed of 1 millimeter per second. So how long time will you take? 10 seconds?
Yes.
Yeah. And then let's say the system, the deposition head takes 5 seconds to come back to its initial location. So 10 second plus 5 second, which is 15 seconds. After 15 seconds, the laser will come back to its initial location. So it is not only the deposition time, but also ideal time between two consecutive layers. Now, things can be different. Like, for example, if you do not want to come back to the initial location, instead, you go from start to end, and while depositing the next layer, you are going in the opposite direction. That means your end location of the first layer is now the starting location of second layer. Then there is no ideal time, right? So there are many things, not only the process parameters, but also the printing strategy or the tool path is also very important for defining the time between two consecutive layers or the total simulation times. And I completely agree with you that significantly affects the thermal cycle.
Yes, the thing is, when I have seen multiple simulation papers, somebody is saying the second reheat cycle temperature will go above the currently solidifying melt pool because it is already has some heat, and when you are reheating it, it will overshoot the temperature of overshoot a certain amount of temperature. But certain papers are saying no, it cannot overshoot and it will always be in the decreasing trend. So but the time lag which they have used is different. So I was just asking, yes, whatever you said, scanning strategy and all. So when you model, you have to define which size you are modeling and after which time the laser comes back, right? And
Correct.
okay.
And also, I think, your observation is correct. And sometimes it's unfortunately true that in the published papers, people do not provide the full information, right? So when they say temperature, we need to see temperature at what location, right?
Mhm.
So if you are comparing between the peak temperature while depositing first layer and peak temperature in second layer while depositing second layer, then you are comparing one thing. And in contrast, if you are comparing peak temperature in the first layer while depositing first layer, but you are
Hmm.
comparing that with peak temperature in the first layer while depositing second layer, these two comparisons are completely different, right? So it also depends on what are the temperatures where we are comparing, whether we are comparing on the top surface or somewhere in the middle of the surface. Temperatures can vary.
Yes, yes. Correct. Okay, I got it. And I had one more small question, that the G and the R map, I know we take it like the two axes, but the G, R and the cooling rate, are they independent? Not the cooling rate, but the G and the R axis, are they mutually independent? Because R would be a function of thermal undercooling, radial as well as constitutional. So just by the G and R, like laser velocity v cos theta, can we say that it's like completely two independent axes and measure the properties?
Yes, G and R are completely two different independent variables. Why? As you correctly pointed out, that R, solidification growth rate, is a strong function of the scanning speed. Okay, so I don't know whether you know about Shindoku's welding metallurgy book. There, Shindoku showed that the formula is solidification growth rate is equal to scanning speed times cos theta, where theta determines the angle normal to the molten pool boundary, right?
Yes.
So if you take, to the trailing edge of the molten pool on the top surface at the mid width, then theta is 90 degree, right? So cos 90, theta is 0 degree. So cos 0 degree is 1. That means solidification growth rate is exactly equal to velocity, scanning speed. Okay. So solidification growth rate essentially indicates that how fast you are solidifying or how slow you are solidifying, which is of course related to the scanning speed. But temperature gradient is very different. Temperature gradient is capturing the effect of both processing condition as well as the material property, the two-phase Massey zone property, which is coming from the phase diagram. So one represents undercooling, another represents the solidification growth rate.
Okay.
So I will probably encourage you to see Shindoku's welding metallurgy book. I think this is the best book to explain this. And
Okay.
the picture that I took also from Shindoku's book.
Yeah.
Yes. Sure. Thank you.
Great. Thank you, Tuhin. Thank you all for attending the webinar today, and we are looking forward to seeing you all next time. So we have a series of tech talk scheduled. So thank you. That's all for today.
Thank you. Bye.
Bye-bye.